Hello viewers, in today's session we are going to discuss a very important and conceptual problem from limits, right? And here we have to evaluate this limit, that is limit x tends to 1, and we have the function x cube minus greatest integer of x divided by x raised to 4 minus greatest integer of x, right? So here we'll see whether the limit of this function involving the greatest integer function when x tends to 1, it exists or not. So for the existence of limits, what we will do, we'll find out the right hand limit and the left hand limit of this function when x tends to 1. Right? So first we'll find out the right hand limit and then we'll find out the left hand limit. Now before finding out the limits, let us quickly revisit this function, that is greatest integer of x. Right? Now see, greatest integer of x is defined as greatest integer of x is greater than or equal to n and less than n plus 1, where n is some integer, right? So for instance, if we take say x is equal to 2.5, then what is the greatest integer of 2.5? So this is obviously 2, because 2 is the greatest integer less than 2.5, right? So we can use this inequality to illustrate this expression. So we have 2 here, n is 2 because this is n. So we have n less than or equal to, here we have greatest integer of 2.5 and here we have 2 plus 1, right? So we can write now 2 less than, here we have greatest integer of 2.5 is simply 2 and here we have 2 plus 1, 3, right? And similarly, if we have a negative number, say minus 1.5, right, then the greatest integer of minus 1.5 is equal to minus 2, because minus 2 is the greatest integer less than minus 1.5, right? So writing this expression in terms of this inequality, we can now write minus 2, then here we have less than or equal to greatest integer of minus 1.5 and here we have minus 2 plus 1, right? So we have minus 2 and here less than or equal to this expression is minus 2 and here we have minus 1, right? And we know that the greatest integer of any integer, say greatest integer of 2 is simply 2 and greatest integer of minus 2 is minus 2 and greatest integer of 0 is 0, right? So let us come to our problem and let us find out the right hand limit. So the notation for right hand limit is limit x tends to 1 and here we put a positive sign and here we have the function f of x. So we can take this function as f of x. So now what we will do, see here we have x is equal to 1 and we'll take 2 points in the neighborhood of x is equal to 1, one towards the left and one towards the right. So the left point or the left neighborhood is given by a 1 minus h and the right neighborhood is given by 1 plus h, right? So when we approach towards 1 from the right of x is equal to 1, then we have this point 1 plus h, right? So we'll do x is equal to 1 plus h. So we'll make this substitution, and when x tends to 1, then obviously h tends to 0, and this quantity h is infinitesimally very small, right? And this is greater than 0 and 1. So h is a very small quantity. So now writing this limit in terms of h, so we have right hand limit as limit, and here for x tends to 1 we have now h tends to 0, and we can write f of x, x is 1 plus h, right? Okay, so now we'll substitute 1 plus h in this expression. So we have limit h tends to 0, and f of 1 plus h can be obtained by replacing x by 1 plus h. So we have 1 plus h cube minus greatest integer of 1 plus h, and here we have 1 plus h raised to 4 minus greatest integer of 1 plus h, right? So now we have to evaluate this limit. See, whenever we come across with functions like greatest integer function or fractional part function, we cannot directly substitute h, the value of h as 0 over here, right? So what we do, we make use of the definition of greatest integer function. Now let us consider this quantity. So see, 1 plus h. Now see, here h is infinitesimally very small, right? So when we add h to 1, then the value of this expression 1 plus h is slightly greater than 1, right? But it remains less than 2. So by definition of greatest integer function, the greatest integer of 1 plus h should be equal to 1, because 1 plus h, this quantity is slightly greater than 1 and it is less than 2. So 1 plus h, it lies between 1 and 2. So the greatest integer that is less than 1 plus h is 1, right? So replacing this quantity by 1 and this quantity by 1, we can now write limit h tends to 0, and we have 1 plus h cube, and here we have minus 1, and here we have 1 plus h raised to 4 minus 1. So now we have this rational expression in terms of h. 1 plus h cube minus 1, 1 plus h raised to 4 minus 1. So now if we here if we take h is equal to 0, then see the expression becomes 1 plus 0 cube minus 1, and here we have 1 plus 0 raised to 4 minus 1. So this is 1 cube. 1 cube is 1, here we have minus 1, then 1 raised to 4 is 1, and here we have 0 over 0, right? So here we have 0 over 0 form, so we can easily apply the L'Hopital's rule here, right? We can also expand 1 plus h raised to 3 and 1 plus h raised to 4 by simply using the binomial theorem, right? But here we'll prefer to use the L'Hopital's rule. So what we will do by applying the L'Hopital's rule, we'll differentiate the numerator and denominator with respect to h. So the derivative of here we have d by dh of 1 plus h cube minus 1, and then we have d by dh of 1 plus h raised to 4 minus 1, right? Okay, so now the derivative of 1 is 0, and here also the derivative of 1 is 0. So the derivative of 1 plus h cube is given by 3 times 1 plus h square, and by chain rule the derivative of 1 plus h is simply 1. And here we have the limit notation, and the derivative of 1 plus h raised to 4 is 4 times 1 plus h cube, and here by chain rule the derivative of 1 plus h is 1, right? So now see, we have limit h tends to 0 3 by 4, and here this quantity get cancelled with this one, and here we are left with only power 1, right? So we have 4 times 1 plus h. So now taking h is equal to 0, here we have 3 by 4 times 1 plus 0. So this is 3 by 4, right? 4 times 1 is 4. So the right hand limit of this function when x approaches to 1 is given by 3 by 4. So let us find out the left hand limit. So the notation for the Left hand limit is given by limit x tends to 1, and here we put a negative sign here, and we have f of x. So now when x approaches towards 1 from the left side of 1, then we come close to this point, that is 1 minus h. So we'll take here x is equal to 1 minus h, and again h is infinitesimally very small, and it lies between 0 and 1. And here when x tends to 1, then h tends to 0. So now expressing this limit in terms of h, the left hand limit is given by limit h tends to 0, and we have f of 1 minus h, right? Okay, so now we'll find out the value of f of 1 minus h by taking or replacing x by 1 minus h. So we have 1 minus h cube, then we have here greatest integer of 1 minus h, then we have here 1 minus h raised to 4 minus greatest integer of 1 minus h, right? Okay, now again the same thing, we cannot substitute directly h is equal to 0 in the expressions containing the greatest integer function, right? So what we will do, we'll separately find out the value of greatest integer of 1 minus h. Now see, in when we have calculated the right hand limit, we had 1 plus h. Here we have 1 minus h. So it means when we subtract h from 1, then this expression 1 minus h is slightly less than 1, but it is greater than 0, right? Because h is less than 1, so 1 minus h remains a positive quantity. But 1 minus h is slightly less than 1, but it is always greater than 0. So the greatest integer of 1 minus h should be equal to 0, right? Because the greatest integer less than 1 minus h is 0. So now we can replace this quantity and this quantity by 0 here. So we have the left hand limit, limit h tends to 0. We have 1 minus h cube minus 0. And here we have 1 minus h raised to 4 minus 0. So now we have simply limit h tends to 0. And here we have 1 minus h cube divided by 1 minus h raised to 4. So this quantity get cancelled with this one, and here we are with only power 1. So this is limit h tends to 0, and we have 1 over 1 minus h, right? Okay, now taking h is equal to 0, here we have 1 over 1 minus 0. So this is 1 over 1, that is 1. So the left hand limit is equal to 1, right? So yes, this is how we can calculate the right hand limit and left hand limit. And here it is interesting to note that the right hand limit and the left hand limit both are finite, right? And both exist. So these two are a very important thing here. So the right hand limit and left hand limit both are finite and they exist, right? But they are not equal. So left hand right hand limit is not equal to left hand limit. And the condition for limit to exist is that the right hand limit and the left hand limit should be equal to each other. Besides, they must be finite and they must exist, right? So the in this case, the right hand limit and left hand limit, although they are finite and exist, but they are not equal to each other. So we can claim that the limit of this function, it does not exist. It does not exist when x tends to 1, right? So this is how we can solve these type of problems. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from limits, right? And in this session we are going to discuss this limit, that is limit x tends to 1, x raised to 5 minus fifth power of greatest integer of x divided by x raised to 4 minus fourth power of greatest integer of x, right? So in this class we'll see whether the limit of this function involving the greatest integer function it exists when x tends to 1 or not, right? So for the existence of limit of a function, what we have to do, we have to separately find out the right hand limit and the left hand limit, right? And we see whether the right hand limit exists and it is finite. Similarly, we see whether the left hand limit exists and finite, and if right hand limit is equal to the left hand limit, then we claim that the limit of the function at the given point it exists, right? So let us examine the limit of this function when x approaches to 1 by finding out the right hand limit and the left hand limit. So let us take this function as f of x, right? And the notation for right hand limit is the limit x tends to 1, and here we write a positive sign, and here we have f of x. So here we have x is equal to 1, and when we approach from x is equal to 1, from the right of x is equal to 1, then we reach at a point which is very close to x is equal to 1, and this point or this neighborhood may be taken as 1 plus h, right? And similarly, when we find out the left hand limit, we approach towards x is equal to 1 from the left of x is equal to 1, right? And we take a point in the left neighborhood of x is equal to 1, and this point may be taken as 1 minus h, right? So 1 plus h is obviously greater than 1, and 1 minus h is less than 1, right? So now we'll take x is equal to 1 plus h, right? And here this quantity h is infinitesimally very small, and it lies between 0 and 1, right? So when x tends to 1, then h tends to 0, right? So now the right hand limit can be written in terms of h as the limit. Here we have h tends to 0, and here we have f of x. X is 1 plus h, right? Okay, so now let us find out the value of f of 1 plus h by replacing x by 1 plus h, right? So we have x raised to 5, so here we have 1 plus h raised to 5. Then we can have greatest integer of 1 plus h raised to 5, and here we have 1 plus h raised to 4 minus greatest integer of 1 plus h raised to 4, right? So now we have to evaluate this limit when h approaches to 0, right? Now see, here we have greatest integer function. So first we have to take care of this greatest integer function, because greatest integer function is a very special function, and whenever we come across with this greatest integer function in limits, then we cannot directly substitute h is equal to 0 over here, right? So what we will do, will apply the definition of greatest integer function here. So see, 1 plus h, here we have greatest integer of 1 plus h. So 1 plus h, because h is a very small quantity, right? So when we add h to 1, then 1 plus h is slightly greater than 1, but it is always less than 2, right? So it means 1 plus h, it lies between these two integers 1 and 2, and from the definition of greatest integer function, we can say that greatest integer of 1 plus h should be equal to 1, right? because 1 is the greatest integer less than 1 plus h, right? So now greatest integer of 1 plus h may be replaced by 1. So here we have a limit h tends to 0 and 1 plus h raised to 5 minus 1 raised to 5, and here we have 1 plus h raised to 4, and here we have 1 raised to 5, right? And 1 raised, here we have 4, so this is 1. So we have limit h tends to 0, 1 plus h raised to 5 minus 1, and here we have 1 plus h raised to 4 minus 1, right? So now we have to evaluate this limit, right? So we have already got rid of this greatest integer function by taking greatest integer of 1 plus h as 1, right? Okay, so now to solve this limit, we have a variety of methods, but here we'll make use of the famous L'Hopital's rule, right? Because see, when we take h is equal to 0 in the numerator, we have 1 plus 0 is 1, 1 raised to 5 is 1, so we have 1 minus 1, and when we take h is equal to 0 in the denominator, then 1 plus 0 is 1, 1 raised to 4 is 1, and here we have minus 1, so this is 0 over 0, right? So we get the 0 over 0 form in this limit, so we can easily apply the L'Hopital's rule by differentiating the numerator and denominator separately with respect to h, right? So now we have the derivative of 1 plus h raised to 5 minus 1, and here we have the derivative of 1 plus h raised to 4 minus 1, right? Okay, so now the derivative of 1 is 0, here also derivative of 1 is 0, so the derivative of 1 plus h raised to 5, by making use of the power rule for differentiation, we have 5 1 plus h raised to 4, right? And by chain rule, the derivative of 1 plus h is simply 1, and here in the denominator we have 4, derivative of 1 plus h raised to 4 is 4 1 plus h, and here we have 3, 4 minus 1 is 3, and then the derivative of 1 plus h by chain rule is 1, right? So we have 5 over 4, 5 over 4, and here we have the fourth power of 1 plus h, here we have third power of 1 plus h, so cancelling the common powers here, we are left with simply 1 plus h, right? So here we also have the limit notation, right? Here also we have the limit notation, right? Okay, so now we can take here h is equal to 0, so limit h tends to 0, 5 by 4 times 1 plus h is 5 by 4, and here we have 1 plus 0, so this is simply 5 over 4, right? So the right hand limit of this function when x approaches to 1 is given by 5 over 4. Now let us find out the left hand limit. So now we have the left hand limit as LHL, and this is limit. Here we can write x tends to 1, and here we put a negative sign, and here we have f of x, right? So when we calculate the left hand limit, we take x is equal to 1 minus h, as we have already explained here. So we have x is equal to 1 minus h, right? So when x tends to 1, then h tends to 0. So now the left hand limit is limit x tends to 1 minus may be replaced by h tends to 0. And here we have f of 1 minus h, right? So now the value of f of 1 minus h can be obtained by replacing x by 1 minus h. So we have 1 minus h raised to 5, and here we have greatest integer of 1 minus h raised to 5, and then we have 1 minus h raised to 4 minus greatest integer of 1 minus h raised to 4, right? Okay, and here again we have the same situation. We have the greatest integer function, and we cannot directly substitute h is equal to 0 over here, right? Okay, so now we'll make use of the definition of greatest integer function. So this quantity 1 minus h, because h is positive quantity, right? And when we subtract h from 1, then this number is slightly less than 1, but it is greater than 0, right? Okay, so 1 minus h, it lies between 0 and 1, and the greatest integer of 1 minus h is equal to 0, right? Because the greatest integer which is less than 1 minus h is 0. So now here we have limit h tends to 0, and we have 1 minus h raised to 5, and here this quantity is 0. So we have 0 raised to 5, that is simply 0, and here we have 1 minus h raised to 4 minus 0 raised to 4. So now we have limit h tends to 0, 1 minus h raised to 5, because this is 0, this is 0, and 1 minus h raised to 4, right? So now here this term get cancelled. Here we are left with only the 1 power of that is 1 minus h. So we have limit h tends to 0, 1 minus h. So now we can take h is equal to 0. So this is 1 minus 0, that is 1, right? So here's the left hand limit is given by 1. So we can see that the right hand limit and the left hand limit both exist, right? So here both the limits exist and they are finite. But the important thing is that right hand limit is not equal to the left hand limit, right? So these two limits are not equal to each other, because 5 by 4 is not equal to 1. So we can say that the limit of this function when x approaches to 1, it does not exist, right? So the limit of this function when x tends to 1, it does not exist, because the right hand limit is different and the left hand limit is different, right? So for the existence of limit of a function at a given point, both the limits must coincide, right? And moreover, both the limits should be finite. Hello viewers, in today's session we are going to discuss a very important and conceptual problem from limits, right? And here we have this problem in which we are given a function f of x which is defined as 1 minus e raised to lambda times greatest integer of pi minus sine raised to 10, and here we have greatest integer of fractional part of x for all x greater than 0, right? And for x less than 0, we are given f of x is equal to greatest integer of tan of fractional part of x minus 1. So let us see how we can solve this problem and how we can find out the value of this number lambda, which belongs to the set of real numbers, right? And here we are given that the limit of this function f of x, it exists when x tends to 0, right? And here the square brackets denotes the greatest integer function, and the curly brackets denotes the fractional part function. So to solve these type of problems, we need to use the concept of greatest integer function and fractional part function. So we'll make use of the definition of greatest integer function and fractional part function, right? So we know that the limit of a function exists if the right hand limit is finite and it exists, right? So if the right hand limit is finite and it exists, and the left hand limit also exists and it is also finite, and moreover if both the limits, that is RHL and LHL, both are equal to each other at some point, x is equal to a, then we can say that the limit of the function when x tends to a, it exists, right? So to solve this problem, we'll first find out the right hand limit, then we'll find out the left hand limit, and then we'll equate both the expressions to get an equation in lambda, and then we can find out the value of lambda. So here our point A is 0, and here we have say x is equal to 0. So when we find out the right hand limit, we approach towards x is equal to 0 from the right of x is equal to 0, and we take a point in the neighborhood of x is equal to 0 and towards the right of x is equal to 0, and this point may be taken as 0 plus h, right? And when we find out the left hand limit, we approach towards x is equal to 0 from the left of x is equal to 0, and we take a point in the left neighborhood of x is equal to 0, and this point may be taken as 0 minus h, and here we have 0 plus h. So the notation for the right hand limit is limit x tends to 0, and here we put a positive sign, then we have f of x. So we take x is equal to 0 plus h, and here h is a positive quantity, and it lies between 0 and 1, and h is infinitesimally very small. So when x tends to 0, then h tends to 0, right? So now the right hand limit can be expressed in terms of h, that is the limit. Here x tends to 0 can be replaced by h tends to 0, and here we have f of x. So x is 0 plus h, so here we have h, right? 0 plus h is h, so here we have f of h. Now f of h can be written with the help of this expression, because here x is greater than 0, and when we find out the right hand limit, we utilize this expression for f of x. So f of h may be written by replacing x by h. So we have 1 minus e raised to lambda, and here we have greatest integer of pi minus sine raised to 10, and greatest integer of fractional part of x. Here x can be written as h, and here we have greatest integer function. So now we have to evaluate this limit. So here we have h tends to 0, right? And whenever we have the functions like greatest integer function and fractional part function, we cannot directly write h is equal to 0 over here. So we'll make use of the definition of greatest integer function and fractional part function. So we know that the fractional part of x is defined as x minus greatest integer of x. So here we have fractional part of h. So fractional part of h can be written as h minus greatest integer of h, right? Okay, now see, this h is infinitesimally very small, right? So this h is very small, so h is greater than 0, but it is less than 1. So the greatest integer of h is equal to 0. So here we'll write 0. So we have a fractional part of h is equal to h minus 0, that is equal to h, right? Okay, so now here we have greatest integer of h. So greatest integer of fractional part of h. So here we have fractional part of h, and fractional part of h is equal to h. So here we have greatest integer of h, right? Now greatest integer of h is 0. So now here we have 0, right? So this term, that is fractional, that is greatest integer of fractional part of h is 0. So now we have this limit h tends to 0, we have 1 minus e raised to lambda, and here we have greatest integer of pi minus sine raised to 10, and here we have 0, right? And sine 0 is equal to 0. So the sine raised to 10, 0 is equal to 0, right? So this term is also equal to 0. So now we have limit h tends to 0, 1 minus e raised to lambda, and here we have greatest integer of pi minus 0, right? Now see, this expression is independent of h, so we can remove this limit sign or the limit symbol. So now we have only this expression. So this is 1 minus e raised to lambda times greatest integer of pi, and we know that the value of the approximate value of pi is 3.14. So the greatest integer of pi is greatest integer of 3.14, that is equal to 3. So here we have greatest integer of pi is equal to 3. So now we can write 1 minus e raised to 3 times lambda. So the right hand limit of this function when x approaches to 0 is given by 1 minus e raised to 3 times lambda. So now let us find out the left hand limit. So the notation for left hand limit is limit, and here we have x tends to 0. We put a negative sign over here. Then we have f of x. So when we approach towards x is equal to 0 from left of x is equal to 0, then we have a point in the left neighborhood, that is x is equal to 0 minus h. So when x tends to 0, then h tends to 0. So now writing this left hand limit in terms of h, we can now write limit h tends to 0, and here we have f of 0 minus h. So now we have limit h tends to 0 and f of minus h, right? Okay, so now here we have the function that is for x less than 0, f of x is greatest integer of tan of fractional part of x minus 1. So now we have limit h tends to 0, and here we have the greatest integer of tan of fractional part of minus h, and here we have minus 1, right? Okay, so now let us take this expression, that is the fractional part of minus h. So we have just seen that the fractional part of x is equal to x minus greatest integer of x. So fractional part of minus h is minus h minus, and here we have greatest integer of minus h, right? Okay, now greatest integer of minus h. See, h lies between 0 and 1. So if we multiply this inequality throughout by minus 1, then we can see that we have 0. The direction of the inequality get reversed. So here we have minus h, then we have minus 1. So we can rewrite this inequality as minus 1, minus h, and 0. So this inequality indicates that minus h, it lies between minus 1 and 0. So here we have 0, here we have minus 1. So minus h, it lies somewhere between minus 1 and 0. So the greatest integer of minus h should be equal to minus 1 by definition of greatest integer function, right? So now we have minus h, and here we have minus and minus 1. So this is minus h, then this is plus 1. So this is 1 minus h. So the fractional part of minus h is equal to 1 minus h. So now we can write the left hand limit as the limit h tends to 0, and here we have greatest integer of tan of fractional part of minus h. So fractional part of minus h may be replaced by 1 minus h. So here we have tan of 1 minus h, and here we have minus 1, right? So now h tends to 0. So here we have tan of 1 minus 0 minus 1. So this is the tan of 1 minus 1, right? So the left hand limit is equal to a tan of 1 minus 1. So now we have right hand limit as 1 minus e raised to 3 lambda, and the left hand limit is equal to tan of 1 minus 1, right? Now since the limit of this function, it exists when x approaches to 0, so we must have right hand limit is equal to left hand limit. So now we can equate these two quantities. So we have 1 minus e raised to 3 lambda, then we have tan of 1 minus 1. So now we have an equation in lambda and we have to solve it. So we can take this 1 to this side. So we have minus e raised to 3 lambda is equal to tan of 1 minus 1 minus 1. So this is tan of 1 minus 2, right? And now multiplying both sides by a negative sign, we have here positive. So this is e raised to 3 lambda, and here we have 2 minus tangent of 1, right? So now taking the natural log of both sides, we have log of e raised to 3 lambda, then we have log of 2 minus tan of 1, and this is 3 lambda log of e, that is log of 2 minus tangent of 1, right? So log of e is equal to 1. The natural log of e is 1. So here we have simply 3 lambda is equal to natural log of 2 minus tangent of 1, right? So we can now write lambda is equal to 1 over 3 times the natural log of 2 minus tangent of 1, right? So this is the required value of lambda. So viewers, here we have obtained the value of lambda as 1 by 3 and natural log of 2 minus tan of 1. So here it is interesting to note that if we take the approximate value of tangent of 1, this is tan 1 radians, and we know that 1 radian is approximately equal to 57 degrees. So tan of 1 may be taken as 1.55, right? So this is the approximate value of tan of 1. So tan of 1 is approximately 1.55. So substituting this value over here, the value of lambda can further be simplified. So we have 1 over 3, and here we have natural log of 2 minus 1.55. So now we can simplify it. 1 over 3 natural log 2 minus 1.55 is 0.45, and this is 1 over 3 natural log of 45 over 100, right? And if we reduce it into the lowest term, then we have here 5 times 945. This is 5 times 20. So we have 9 over 20, right? So this is the approximate value of lambda, that is 1 over 3 natural log of 9 over 20.